All right, let's dive right in. We're going to take a look at something that's been a cornerstone of physics for over 100 years, and we're going to question it. We're about to see a really famous experiment in a totally new light, all thanks to some pretty mind-bending ideas from our source material today.
You know, for more than a century, we've had this one specific answer to a super famous physics puzzle. But what if that answer was just a clever patch, a workaround? What if the real solution isn't some new rule, but a completely different way of looking at reality itself?
So, let's set the scene. It's the 1880s, and we're talking about the famous Michelson-Morley experiment. Back then, scientists thought light needed something to travel through, this mysterious stuff they called the ether. So, this experiment was designed to do one thing: detect the Earth moving through that ether. The setup was pretty clever. Split a beam of light, send the two halves on different paths, and then bring them back together. They totally expected one to be a little bit late, because of the motion. But nope, no delay. The light beams always came back at the exact same time. And this result? It completely baffled everyone.
So, what was the fix? Well, the solution that eventually became part of Einstein's special relativity was pretty wild. It's called Lorentz contraction. The idea is that an object in motion literally gets shorter in the direction it's moving. And this physical squishing perfectly explains why the light beams always arrived together. It's a brilliant fix, right? It makes all the math work out. But our source today is asking a really provocative question. What if it's not a fix at all? What if we've just been misunderstanding something way, way deeper?
Okay, so to really get our heads around this new idea, we need to think about two totally different ways of seeing the universe. Our source material calls them the camera eye and the God's eye.
So, the camera eye, that's pretty much how we see the world every day. It's the here and now, our familiar 3D world. It's our local, subjective view from inside the experiment. But then there's the God's eye. This is a view from outside of what we call 4D spacetime. So that's the 3 dimensions of space plus the dimension of time, all at once. And from that perspective, you can see an object's entire journey, its past, present, and future, all laid out as one single complete thing. And the source gives us a fantastic analogy for this. It's like we're used to looking at a flat Mercator map, that's our 3D camera eye view, but the actual phenomenon is happening on a globe, which is 4D spacetime. Think about it. A straight line on a globe, like a flight path, looks like a weird curve on a flat map. So what do? We invent all these complicated rules to explain why it's a curve, instead of just, admitting we're looking at the wrong kind of map in the first place. So what does happen when we switch our view and look at the globe of spacetime? Well, this is where it gets really cool. The author of our source actually built a special tool in Blender, the 3D software, to do exactly that. It lets us see the Michelson-Morley experiment from that God's eye perspective. Okay, I know this might look a little weird at first, so let me walk you through it. What you're looking at here, in this Blender model, is the entire experiment moving through time. That vertical axis, that's not up and down space, that's the arrow of time. The experiment begins at the bottom, in the past, and travels upwards, into the future. Those orange and blue lines you see, those are the paths of the light beams as they travel through spacetime. And that white cage, that represents the actual physical mirrors of the interferometer, chugging along from the past into the future. So, the light starts at the bottom, bounces off those mirrors, and then comes back together. Now, watch this. As we shift our God's eye perspective, you'll see this yellow shape. This highlights something absolutely crucial. It's showing us the exact points in space-time where each bit of light hits a mirror. Now, from our normal everyday camera eye view, we would just assume all those reflections happen at the exact same instant, right? Simultaneously. But from this God's eye view, well, we're about to see that's not what happens at all.
Here's the big reveal. The reflection points don't form a flat circle. They actually form a tilted ellipse through spacetime. Look closely. The reflections are not simultaneous. The light that's traveling in the same direction as the experiment has to go further up into the future to catch up to its mirror. And the light going the other way, it hits its mirror earlier in time. They're all happening at different moments.
And here's the really mind-blowing part. Check this out. On the left, you've got the interferometer moving pretty slowly, and you can see that reflection ellipse is almost flat. But now look at the right. This is a fast-moving one. See how much that ellipse tilts? It's dramatic. The faster you go through space, the more these reflection events get stretched out and skewed through time. So when you see it like this, from this geometric perspective, well, of course the light beams arrive back at the detector at the same time. It's not a mystery that needs a special rule. It's just a simple, unavoidable fact of geometry in 4D spacetime. You don't need to invent a rule about physical contraction because the very shape of space-time forces this to happen. It's baked right into the geometry.
Now this is way bigger than just a neat new way to explain an old experiment. This whole geometric viewpoint is actually a really serious critique of the way we've been thinking about relativity for over a century.
And yeah, the source material does not pull any punches here. It calls the standard interpretation a disorder, where the subject and object are completely reversed. It's like, instead of us being subject to the laws of the universe becomes this slave that has to warp and contract itself just to make our measurements work out. It's putting the observer on a pedestal.
It's a fantastic analogy, really. It's like the old shift from the Ptolemaic, Earth-centered model of the solar system to the Copernican one. The standard view of relativity can feel a little bit Ptolemaic, right? I am stationary, and the universe contracts around me to make my math work. But this new geometric God's eye view, that's Copernican. It says, no, space-time has a fixed geometric structure, and I'm the one moving through it. Everything I observe is just a consequence of that geometry.
And this is where it gets really wild. Because if this geometric view is correct, it leads to a conclusion that is, well, it's completely radical. It's almost heresy in modern physics. It's the idea that we can actually detect our absolute motion through the fabric of space-time itself.
The source gives us another great analogy here. Think about a submarine moving through an ocean current. To figure out its speed relative to the water, it can send out active sonar pings in all directions. By timing how long it takes for those pings to come back, it can spot an asymmetry. The pings that go against the current will return at a different time than the pings that go with the current. And from that tiny difference, the sub can calculate its exact speed through the water.
Okay, so this leads to a brand new concept the source calls field speed. And just to be clear, we're not talking about your speed relative to the sun or the Milky Way or anything like that. No, this is your absolute velocity relative to the fundamental structure of space-time itself, the cosmic ocean that our little submarine Earth is traveling through.
So that leads to the big question, right? If that tilt in the reflection ellipse is a real physical thing, then could we actually build an instrument to measure it? Could we use that measurement to figure out our own absolute speed through the cosmos?
And how would you even do that? Well, the process would basically be like that submarine sonar. First, you ping the universe by sending out light signals in all directions. Then you listen for the return signals, and you'd need to measure them with incredible precision, looking for any tiny asymmetries in their timing or arrival angle. And finally, you calculate. You take that distorted data, that geometric skew, and use it to derive your absolute field speed vector.
And let's be super clear here. This idea completely flies in the face of a central pillar of special relativity. According to this model, absolute motion isn't undetectable. It's not this unknowable thing. It's a direct, calculable consequence of space-time geometry, a fingerprint left on the light that's hitting our detectors, telling us exactly how we're moving through the cosmos.
And that leaves us with one last really provocative question to think about. For over 100 years, we've believed that a famous experiment found nothing, and we built one of the main pillars of modern physics on top of that null result. But what if it was never nothing? What if the evidence of our own cosmic velocity has been there the entire time, just hiding in plain sight, waiting for us to stop staring at the flat map and finally look at the globe?
So if this has got you thinking and you want to dive deeper into this rabbit hole, you should definitely check out the original source material. You can even play it with the Blender add-on yourself. We've got the link right here. It's a perspective that, hey, might just change how you see, well, everything.